Okay, welcome back, Chemistry 30. Hopefully this is part 2 of the video for the booklet 16.3. Hopefully you had time to plot that graph, and now we'll look at the two questions that correspond to that. So first of all, it asks for what type of energy is involved there, and then calculate the heat involved for each of those sections on the graph. You may have expected the graph to be just a straight line increasing graph, but of course it raises up to 0 and flat lines, raises up to 100, flat lines, then raises up to 120. So there are 5 different sections in that graph, and we'll analyze each of those sections. Before we do that, just remember that temperature is a measure of kinetic energy. So however fast the molecules are moving and the energy involved with that, that is temperature. So a change in energy is indicated by a change in temperature. So the first part of that graph, going from -20 to 0, since the temperature is increasing, that must mean kinetic energy is increasing as well, since the temperature is moving. And to calculate the energy there, we've done that before. Whenever we have a movement in temperature, that means that's kinetic energy. So Q equals Cm delta T. C for specific heat of solid water, 2.03 joules per gram degree C. And of course we're told in the experiment that we had 180 grams of water, and going from -20 to 0, that's a temperature change of 20 degrees C. So that gives us 7,308 joules. That's the amount of energy that's involved with that first part of the reaction. Second part there is a flat line at 0 degrees, and the temperature is not moving. Even though we're adding heat to it, the temperature is not moving, so that must mean it's not increasing in kinetic energy. The only other energy we can think of there is potential. So it's increasing potential energy. The molecules are absorbing the energy to hopefully gain movement to go past that change in state, going from solid to a liquid. Now to figure out this part, we're told so 180 grams is equivalent to 10 moles of water, and this process going from solid to liquid is fusion. And earlier we saw that the enthalpy of fusion for ice, going from solid to liquid, plus 6.01 kilojoules for every 1 mole. So we use that number there. We have 10 moles though, so we'll multiply that by 10. That works out to be 60.1 kilojoules. If I convert that into joules so we compare all these values, 1 kilojoule is 1,000 joules, so that's 60,100 joules in total. Okay, so no movement in energy, so it must be potential energy that's increasing. And then once we get back to this, the next spot there, going from 0 to 100, the temperature of course is increasing. It's going from 0 to 100. So we can go back and figure out the energy involved the same way we did back up here. So this time of course the water is in the liquid state, so I use the 4.184 joules per gram degree C. 180 grams, the temperature change is 100, so 75,312. So much more energy involved there, and you can see that it's much more because the time in order to go through this part of the heating up is larger than the other ones. Then of course at 100, it stays at 100 for a while, so that must mean there's no kinetic energy increasing, it's potential energy again increasing. And this time going from liquid to vapor, liquid to gas, enthalpy of vaporization 40.7, since we're using water there. So 40.7 kilojoules for 1 mole, therefore for 10, that's 407 kilojoules, or converting that into joules by multiplying by 1,000, 407,000 joules. And you can see that's, I think, the biggest area on the graph, which makes sense because it involves the most of the energy. And then the last phase there, going from 100 to 120, so we have kinetic energy increasing there, so we can use our other way of converting it. Of course water is in the gas state here, so we have to use the specific heat for water vapor, 2.01 joules per gram degree C, 180 grams, and 20 degrees C. So that works out to be 72,000 7,236 joules. So there you have it. During those 5 states there, exactly what is occurring. If it's a change in energy, a change in temperature, that means kinetic energy is increasing. Or if it's just hanging around at the same temperature and yet we're still adding heat, that must be a change in potential energy. Okay, so we'll answer the couple of questions involving that, then we'll move on to part 3 after this. So if we're looking at going backwards, the freezing point of water is 0, and it of course is exothermic. When going from liquid to solid, it's exothermic, as indicated in this diagram. Liquid to solid, we're releasing heat in that case. Describe how the potential energy is changing. So going the opposite way, back here, if we're going from solid to liquid, potential energy is increasing. So if we're doing vice versa, going from liquid to solid, potential energy must be decreasing. So temperature isn't changing, so the molecules are slowing down, etc., and they're losing stored energy to hopefully reach the solid stage. And then lastly, how did the kinetic energy of the water molecule change when this occurs? There's no change in energy because, again, the temperature is not moving. Okay, so that'll be it for part 2. Hopefully you can join me again for part 3 shortly.